With the respiratory system, it's important to note that there are four stages of respiration. The first stage of respiration is pulmonary ventilation. The second stage is external respiration. The third stage is transport of gases through the blood. And the fourth stage of respiration is internal respiration. Now, internal respiration is where it actually starts to count. So if you're thinking about, for example, the passage of oxygen, oxygen is ventilated into the lungs. It is then passed through the walls of the alveoli into the blood. That's external respiration. It is then transported through the blood, and then it is passed from the blood into the tissues of the body, and that is internal respiration. And that's where it actually counts. So the whole point of the respiratory system actually is not just to get air into the lungs, but it's eventually to get oxygen to the cells of the body. And you must also remember, and I would suggest writing it down, that carbon dioxide follows the opposite path from the cells eventually out through pulmonary ventilation out of the body. So basically the same four steps, but backwards, if you will. So the first thing we'll be doing in class is covering some homeostatic imbalances or some disorders of the respiratory system so that you can kind of engage with the four steps and think about what could go wrong at each of the steps partially. And then we'll move on with this sort of information. So the first thing we're going to be covering is the idea of the basic properties of gases. First of all, there is Boyle's law, which we will define as PV equals K, which defines how it is that pulmonary ventilation actually works. Next, we'll be discussing two laws that infer the way that gases are exchanged in the body. So gas exchange in the body is governed by Dalton's law and by Henry's law. So Dalton's law of partial pressures is that the sum of partial pressures equals the total pressures. So what we're looking at here is partial pressure of, for example, nitrogen, and this is how we denote it, P sub N2. Partial pressure of oxygen, P sub O2. Partial pressure of carbon dioxide, P sub CO2, and then the partial pressure of other substances, such as water in the air, is also listed. So the partial pressures equals your total pressure. So what we're specifically looking at here is air, the actual air, and you can see that 78% of the air is nitrogen, and the partial pressure of nitrogen is 592.8 millimeters of mercury. Oxygen takes up 21% of the air, so the partial pressure of oxygen is 159.6. It's interesting to note that when we look at what's happening with air, so here are the numbers copied out from the previous screen, more or less. You can see that some things have changed. For example, we are including just the water here instead of other. And then take a look at this. So this is the percentage and then the partial pressure of the atmospheric air. And then over here we have the approximate percentage and partial pressure of alveolar air. We're going to go over these numbers more in class. There's only a few that we're really going to be paying attention to, but I want you to kind of look at it as a whole right now and think about all these different numbers. Wouldn't advise copying them all out. We're going to be concentrating on the oxygen story and on the carbon dioxide story, and we're specifically going to be looking at partial pressures of both of those gases. But it is informative to notice kind of like the total percentage of structures in the air. Okay, so that's Dalton's law. And again, the partial pressure is the pressure exerted by each gas in a mix. So let's take a look at Henry's law. Henry's law is the concept that a greater concentration of gas will go into solution faster than a lower concentration of gas. However, and so also that each gas will dissolve in proportion to its partial pressure. However, this depends on the solubility of the gas. Carbon dioxide is the most soluble, oxygen is next, then nitrogen is nearly insoluble. So, although Henry's law is contingent on the partial pressure of the gas, the solubility counts for quite a lot as well. This is a figure that points to the second and fourth stages of gas exchange, which is external respiration and internal respiration. I'm going to cut these apart here, so we're kind of just looking at the external respiration story. The external respiration is exchange of gases at the level of the lungs. Carbon dioxide will leave the blood and oxygen will enter the blood. This is due just to diffusion. So we're looking at these here. What we're looking at is atmospheric air. Here we are looking at the composition of air inside of the lungs. Here we are looking at the composition of composition of gases inside of the blood as it leaves the lungs and then as it eventually leaves the heart. And here we're looking at the composition of gases as it is headed towards the heart and towards the lungs. I would suggest going into your textbook and studying on these figures. There's quite a lot of information on them, and copying the numbers out into here so that you can kind of get an idea, and we'll discuss this a little bit more in class. There's a lot of numbers here. It looks like a lot of detail, but actually there's a few stories that are just very simple and straightforward and kind of just make sense, but it does take some time to get used to them. So take a look at those numbers before we get to class. And here's the internal respiration story. Internal respiration is the exchange of gases at the level of the tissues. In this case, the gradients are opposite to those in the lungs, so oxygen will be leaving the blood and carbon dioxide will be entering the blood. Again, simple diffusion.